Good morning, Year 10, and welcome to today's lesson. If you could pause the video and complete the low stakes quiz in your exercise book, that would be fabulous. Thank you, and welcome back. You need a green pen. You need to have made sure you put the date, which is actually the 26th by the time you're watching this, and the title, Factors Affecting the Resistance of Electrical Circuits. And now can you go through and mark your answers? So, naming these components, we have a diode, we have a variable resistor, and we have a normal resistor, or a fixed resistor it can be called. What is current measured in? You should have got the answer amps. What is potential difference measured in? Volts. Draw a dot and cross diagram of sodium chloride, and we haven't got an answer that's going to come up for this one, but we should have had Na with square brackets round with the plus, and a chlorine ion where we've got a dot and a cross, and then it doesn't matter whichever one you've chosen to use around the rest, but you must have one where it shows that the electron from the outer shell of sodium has moved across to chlorine, and that must have a minus charge on. So that's what a dot and cross diagram of sodium chloride looks like. Name the organelle that controls the cell. The answer is the nucleus. And name the organ which plants use to absorb water. The answer is roots. Okay, so we should have that out of the way. And on we go to the rest of the lesson. So what we're aiming to do today is we're going to look at the factors that affect the resistance of an electrical circuit. And we need to be able to describe those factors, and we need to be able to experimentally show this. Now, this is one of the required practicals in this module. There are two. We did the other one yesterday. This is a two-parter, and we do part A today, and we'll go on and do part B tomorrow. So this week is going to have been completely experimental. Everything you will have learned this week builds on what we did last week. If you're watching this video and it's the first electricity topic, or you haven't watched for a couple of days, you do need to go back and do them in order. They are all in the classroom. They are all titled appropriately. You should be able to see the order that you need to do them in. Okay, so all the keywords that we're using today: ammeter, voltmeter, resistor, current, potential difference, and resistance. These should all be coming part of your vocabulary now. We come up against them in several lessons. You need to be able to use those words in the correct places. So watch out for those across the lesson. So, resistance, and we need to describe the factors that will affect resistance. So, in outline, anything that slows down electrons is called resistance. Can you write that down? Then we need to think about, well, what else actually in a normal circuit is affecting? And we need to think about, well, what is going to slow those electrons down? And squeezing through a thin wire is going to slow them down more than being able to flow in many different streams through a thick wire. Think about what happens on the motorway when there's an accident and the motorway gets shut from 3 or 4 lanes down to just one. You usually get a traffic jam because the traffic can't flow through one lane as fast as it can 3. So other factors are thickness of the wire. And we actually look at this because a wire is usually a cylinder. We actually, on thickness, would look at the diameter. However, as we are scientists and we look at doing things the most precise way, we want to be as accurate as we possibly can. The better way of talking about this is to talk about the cross-sectional area. Because actually, as you may well know, you can take the diameter, and because of the difference between area and diameter, and remember the diameter and the area of a circle, pi r squared will give us the area, whereas diameter is just 2r. So if we double the thickness of a wire, the cross-sectional area actually gets over 3 times bigger. And so by talking about cross-sectional area, it allows you to be a lot more precise on that. And actually that does help then seeing a relationship between. Other things. So if you're, and again, use the analogy of traffic and think of cars driving down the road, and actually, well, what slows down, what means that it takes longer to get there? If you've got longer to go, it takes longer to drive 20 miles than it does to drive 5 if you're always driving at the same speed. So length of wire, and I know that sounds very simple, but it is absolutely a key part of it. Another one is the actual material. And again, back to the road analogy, think how fast you can drive down a very potholed country road versus a beautifully smooth, freshly tarmacked piece of motorway. Or even think about where it's a very bendy road. No, because that affects length. No, I do think condition of the road is your equivalent to material. And lastly, the other factor that will affect it is temperature. And we know that this affects resistance because that was one of our definitions that we had when we were talking about our ohmic resistance yesterday. So we need to do whatever we can to control this variable when we are experimenting with these, because actually resistance, bearing in mind that resistance is effectively the friction caused by the electrons, we need to minimize any temperature change in order to make comparisons between our ideas. I've just realized I wrote it the wrong way. So control this variable. And that's actually another keyword. We haven't talked about variables for a while. So variables are the things in an experiment that you have the ability to change. And remember, we have the independent variable, which is the variable we are going to change. We have the dependent variable, which is what will change as a result of that. And every other variable should be a control variable that you have to control. So temperature is an example of that. Okay, we're going to go on and do this experiment. And I'd like you, before I go and do this, to pause the video and first of all, draw this circuit. So we've got a circuit with a battery going to the wire, back to the ammeter and back to the battery. And we've got the voltmeter, and this, if you notice, is in parallel across this wire. And what I can do, I can't because it's just a picture. What I will be able to do on the simulator that I've got is I can move where this crocodile clip is on the wire. And so we can effectively vary the length of this piece of wire that we are measuring the resistance over. Okay, once you've drawn that diagram, I would very much like you to draw this table. And I want you to give yourself 8 rows in that table so that we can actually see, we can get enough results to be able to see what's happening there. So I'd like you to pause the video and I'd like you to do that now, please. Okay, going out of PowerPoint and on to the simulator. So here we are. Now we need to be recording the data that we are getting out of this experiment. Oops. I'll make for good sound effects on my video. So we're going to start off. I'm not actually going to set this to 0, and the reason is because the voltmeter is reading other wires, so I'm not necessarily expecting my graph to go through, because I don't truly have the potential difference of 0 distance on my wire. So we're going to start at length of wire is 5. So we've got length of wire in centimetres, 5. The potential difference of that is 0.78 of a volt. And the current is 1.43. Okay. And then we're going to go up to 10. And write that down. So 10 centimetres, 0.88 is a PD. I do appreciate your table said voltage, but I've written it down as PD because that's really what I wanted. But never mind. And our current is 1.24. Now we're going to go up to 20. Now notice up here I'm trying to be as accurate as I can be. So 20 centimetres, and we've now got 1.03 and 0.95. Notice that as our length of wire increases, and we're now going to go to 40, the potential difference is going up and the current is going down. Remember Ohm's law, V equals IR. There is always that relationship between them, particularly in a ohmic conductor. And 60. That's not actually on 60, is it? I need to be on 60, please. Oh, it's really hard to get that. It doesn't want to sit back on 60. Okay, so 60 centimetres, and we've got 1.26 and 0.48. 80. And we've got 1.31 and 0.39. And the last one we're going to do is we're going to take it right up so that it's stretched over a metre, so 100 centimetres. And that is going to be 1.34 and 0.32. Right. So you've now got 7 readings. I'm sorry, I asked you to make room for 8, and actually we didn't do 0, but never mind. So what I'd like you to do now is pause the video, and I'd like you to use V equals IR to calculate the resistance for those. So off you go. Okay, so hopefully you've done that now. I'm just going to show you what I've got on my screen. So I have calculated the resistance, and I've done that by using V equals IR, which means that R equals V divided by I. So I've done 0.78 divided by 1.43. I've come out with 0.55, and I've done that for each set of measurements, and that of course is measured in ohms. Now you will probably have got slightly different numbers because I have always rounded them to 2 significant figures, and I do that because this column and this column, we've only been able to record the data there to 2 significant figures, so there is no reason why we should generate more accurate data by calculating with the data that we had. Okay, now unfortunately I haven't got any graph paper, but I'm just going to show you what this graph would look like. So we've got our length of wire will go along the x-axis, and that's in centimetres. And we've got resistance in ohms going up the y-axis. Now, when you're drawing a graph, even if it's a sketch graph like this one is, because it's on line paper, not graph paper, what I want you to be aware of is that you are always making sure that your gaps are the same. So notice as I go up here, 0.5 going to 1.0, 1.5, the gaps between them are all the same. And if you look here, 10 to 20 to 30 to 40. Now, I haven't got graph paper, but that 5 is slotted in the middle. Now, I've got a reading for 5 because I chose to take slightly non-linear measurements, and there's a reason why I did that. So at 5, I would be plotting a point just above 0.5 because my resistance was 0.55. At 10 centimeters, it had gone up to 0.71. At 20, it was over 1. It was 1.09. And at 40, it was 1.78. Going to be just above there. Now, I hope you can see that even though this is very much a sketch graph, that actually those points would be very, very close to sitting bang on a straight line. And I could draw through those points and I could expect to find out roughly where it hit the 0. And of course, remember that it is hitting 0 there because actually there were other wires involved in this. If there were none, if there had been no other wires, if that potential difference could have been measured really stringently accurately, that 0 was 0, i.e. that there was no wire that we were measuring potential difference over, you would expect it to go through the origin. But that is there, and that hits and intercepts the y-axis there because there were other wires involved. Okay, so with that in mind, and we'll just take a little snip of that actually, because that's quite useful. And we'll go back to our PowerPoint. And so we can answer the question, what would a graph look like? Maybe we can't. Maybe Miss is struggling to operate PowerPoint. Ooh, there we go. Right, now, so if I drop that into there, it's huge. Okay, so what would a graph of this look like? And our answer to that question is going to be the graph should be a straight line. In theory, if we really were measuring the length of wire, it should go through the origin of the graph. But this is hard to achieve practically. Okay, and last bit, what can we conclude from this is that resistance is directly proportional to the length of the wire. And there we go. Okay, I hope you haven't got too many questions on that. This quick video hasn't been too long so far. The next thing you need to go away and do is you need to go and do the practice exam question that I have attached to this lesson. I'm going to give, well, I don't want you to give yourself too long for that. It's 12 marks, so it should only take 12 minutes. Then I want you to come back and we'll go through the mark scheme for that. So pause the video again, off you go and do the exam question, and then come back. Okay, so welcome back. Here we are. We're about to get going through this mark scheme. So this is what we call a level 2 question. So this is assessing you at grades 4, 5 and 6. It's not really pushing up. So this would be at the start of a higher tier paper or at the end of the foundation tier paper. Okay, so the student took measurements using the meters X and Y. I'm hoping we're starting to get to the point that we're confident that the amp meter will be in series and the Y will be the voltmeter. Make sure you're correcting your work with a green pen. Make sure you've done the work and you're not just writing my answers down. Okay, for which length of wire are the readings of this resistance most precise? And the answer is the longest ones. Now, this is a bit of a think about question. And the reason is the longer the wire is, the greater the distance there is for any inaccuracies to be absolved over. Oh, no, sorry, wrong answer. 0.300. The reason behind that is that there is the smallest range. So it's actually the smallest range. And if you look there, here we go from 1.34 to 1.4. Yeah, so that has got a range of 0.08. That has got a range of 0.06. That has got a range of 0.01. That has got a range of 6877, 0.09. There we've got a range of 0.05. And last but not least, 0.07. So that is why that is considered the most precise. Why did the student do 3 tests and calculate a mean? So this is to reduce random error. Now, random errors are ones that where you turn a machine on, for instance, a voltmeter, and for some reason, something's maybe just got stuck in one of the connectors, and actually it gives you a potential difference reading of 7 volts where it should be reading 5. But when you turn it off, you just maybe give the voltmeter a little tap, and suddenly that's been dislodged, and the number goes back to normal. That would be a random error. Okay, next question. Write the equation that links current, potential difference, and resistance. Now, I keep giving you this as a question, and here it is actually coming up in a exam question. You're quite entitled to put it in symbol formula, or you can write it out. Potential difference equals current times resistance. Then we go on to E. Write any equation that you use. So we've got a potential difference of 2.1 and we've got a current of 0.3. So we're going to need to use that equation, and we're going to need to find its resistance. So R equals V divided by I. So that's the equation I'm going to use And then I'm going to do 2.1 divided by 0.3, and the answer is going to come out as 7.0 ohms. 7.0. And the units are there, so I'm not getting a mark for that. So when I'm answering that question, I am getting a mark. I get 1 mark for writing this, mark 1. I get another mark for writing this, and I get a mark for writing the answer. Now, if I get that right, it doesn't matter if I've written anything else. But if I get that wrong, so for instance, if I've rounded and I've got 7.1, providing I've written that down and that, I would have still got marks for that equation. Okay, then we go on and look at the graph. So figure 2 shows a graph. What is the label for each axis? And so we're expecting this to be the same as the graph that I drew. So on the x-axis, we've got, again, we can compare this back to our results. So we know that when it's going up in 0.1s, that is length of wire in meters. And our y-axis is resistance, or mean resistance. Don't have to put that there. In ohms. You must put the units. They are critical. If you don't put those, you cannot get the marks. And last but not least, what conclusion can be made from the graph in figure 2 is that resistance is directly proportional. And that's exactly the same as the conclusion that we drew from the experiment that we did. Sorry if you can hear that noise, but directly proportional to length. Okay, thank you very much for joining me today, Year 10. Make sure that you upload the work, make sure that you've marked that exam question as well as you can and uploaded your work, and I will have a look at it in the evening. Thank you very much.